Welcome to my channel. Today, we're breaking down some powerful machine learning techniques. We're going to look at how we can combine multiple models to make one super smart prediction, and how algorithms can find hidden groups in data all by themselves. So let's dive right in by tackling a really fundamental problem. Why is it that a machine learning model can seem totally brilliant one minute and then fail completely the next? It's a great question. And the answer usually isn't that the algorithm itself is bad. It's actually about this classic dilemma that every model faces while it's training, this constant tug of war between two competing goals. It's called the bias-variance tradeoff. Now, think of it like this. A model with high bias is kind of like an underachiever. It's just too simple. It overlooks the important patterns in the data. But a model with high variance, that's the overthinker. It memorizes everything from the training data, including all the random noise, which makes it totally useless when it sees something new. So you can see the problem, right? The goal is to hit that perfect sweet spot, low bias, so it's accurate, and low variance, so it's consistent. But since pushing one down often pulls the other one up, we need a smarter way to do this. And that brings us to our first major technique, ensemble learning. So instead of building just one model and, crossing our fingers, ensemble methods do something really clever. They're all about the idea that many heads are better than one. They combine the wisdom of lots of models to make a much stronger final decision. And this table really lays out the two main ways to do it. On one hand, you've got bagging. The best analogy is a democracy. You train a bunch of models all at the same time, independently, and then they all get an equal vote on the final answer. On the other hand, there's boosting. This is more like an expert committee. The models learn one after another in a sequence. The first one makes a guess, the second one learns from the first one's mistakes, the third learns from the second one's mistakes, and so on, getting smarter with each step. Okay, so ensemble methods are fantastic for making accurate predictions, but what if that's not what you're trying to do? What if you don't have a specific outcome to predict, but you just want to find the natural hidden structures that already exist in your data? Well, this is where a technique called clustering comes in. And the key thing to get here is that it's a type of unsupervised learning. That's a huge deal. It means we don't give the algorithm any answers up front. We just hand it a pile of raw data and basically say, hey, go find the patterns. This is incredibly powerful for all sorts of things, from figuring out customer segments to analyzing medical images. So, which of course leads to the big question, how on earth can a machine just find these groups automatically? How does it look at a big cloud of data points and figure out which ones belong together? Well, one of the most famous and honestly intuitive algorithms for this is called k-means. All right, let's get into the nuts and bolts of k-means. It's actually a really elegant and, believe it or not, pretty simple process. When you break it down, it all works in this really neat little loop. First, you have to decide how many clusters you're looking for. We'll just call that K. The algorithm then randomly drops K center points into your data. Next, it looks at every single data point and assigns it to whichever center it's closest to. Then, and this is the clever part, it moves each center to the middle of the new group of points it just collected. And that's it. It just repeats those last two steps. Assign points, move the center. Assign points, move the center. Over and over until the groups settle down and the centers stop moving. Okay, but wait a second. This whole thing kind of hinges on that very first step, right? Choosing K. I mean, how are we supposed to know the right number of groups to look for? If we guess wrong, the results could be totally meaningless. Well, thankfully, we don't have to just pull a number out of thin air. There's this really clever technique called the elbow method that helps us find the ideal K for our data. Here's the big idea. We basically test out a bunch of different values for K. We run the algorithm and say, okay, try finding just one cluster, then two, then three, and so on. Each time we calculate a score, this WCSS thing, which is just a measure of how tight and compact the clusters are. A lower score is better. Now, the score will always get better as you add more clusters, but what we're looking for on the graph is the elbow, that exact spot where adding another cluster doesn't really help all that much anymore. It's the point of diminishing returns, and that's our sweet spot. That's our K. Okay, theory is great, but let's make this real. Let's put k-means to work on some actual student data and see what happens. So let's pretend we're working for a college placement office. We've got data on 200 students, and for each one, we know two things: their grades, their CGPA, and their IQ score. Our job is to group them up so we can give them better, more tailored advice for finding jobs after graduation. So what do? We run our elbow method on the student data. We plot the results, we look for that distinct bend in the curve, and Bam! The data itself tells us there's a clear elbow. The optimal number of clusters isn't 2 or 5 or 10, it's 4. The data is telling us there are 4 natural, distinct groups of students in our dataset. And right here is the magic of it. The algorithm didn't just spit out 4 random groups, it found 4 meaningful student personas. Look at this. You've got your all-rounders, high grades, high IQ. You have the hard workers, amazing grades, maybe a lower IQ but super diligent. Then there's the smart but casual crowd, high IQ but maybe their grades don't reflect it. And finally, the group that needs support. Just like that, the college can go from a one-size-fits-all plan to perfectly targeted guidance for each of these groups. So you see, whether we're talking about combining models with ensembles or finding hidden stories with clustering, these aren't just abstract tools. They're ways to get to a much deeper understanding of the story our data is trying to tell us. It really gets you thinking, doesn't it? I mean, if an algorithm can find such specific patterns in a small set of student data, just imagine what other incredible insights are out there hiding in plain sight in the data all around us, just waiting for the right algorithm to discover them.